Hello students, so today I will explain the structural elucidation of α-Pinene and its synthesis. So if we see the structure of this α-Pinene, so this is the structure of α-Pinene which we have to prove. So this is the structure of α-Pinene. Now let's see how we can elucidate its structure. So first of all, its molecular formula that was determined, it was determined to be C10H16. So this was the molecular formula that was determined by the elemental analysis at that time. Now secondly, we determined its double bond equivalent. If we see double bond equivalent, then it is 10 means number of this carbon atom minus number of monovalent atom, that is 16 divided by 2, plus number of trivalent atom divided by 2, and here the number of trivalent atom is 0, so we can write 0 by 2 plus 1. So this is the formula by which we can determine the double bond equivalent. So this comes out to be, 11 minus 8, so it is 8. So 11 minus 8, that comes out to be 3. Now if we see the structure, I have already written the structure and which we have to prove. So if we see the structure, then 3 means here one of the carbon-carbon double bond is present, and this is a monoterpenoid. This is a monoterpenoid as it contains the 10 carbon atom, and this monoterpenoid is the bicyclic one. So 3 double bond equivalent, that is, it means 1 carbon-carbon double bond and 2 cyclic rings are present. Now, so how can we prove this carbon-carbon double bond? So it was proved when this α-Pinene, that was treated with bromine. When it was treated with bromine, then it was found that it forms a dibromo α-Pinene. Means it has one double bond. Along the double bond, 2 bromine atom is attached, and that's why it is forming the dibromo α-Pinene. So what it indicate? It indicate one carbon-carbon double bond. Okay, one carbon-carbon double bond. C double bond C, that is one double bond. Okay, now if we see, then as the molecular formula is C10H16 and it contains one double bond, it is one unsaturation is present. So if we saturate this formula, then we have to add 2 hydrogen atoms. Now adding this 2 hydrogen atom, so this will give C10H18. Now this C10H18, it corresponds to the general formula CnH2n minus 2. So CnH2n, if the general formula is CnH2n plus 2, then it corresponds to the acyclic monoterpenoid. If it has the formula CnH2n, then it corresponds to the one of the monocyclic terpenoid, and if it corresponds to if the formula is CnH2n minus 2, then it corresponds to bicyclic terpenoid. So it means it indicate our this terpenoid or the α-Pinene is bicyclic. So it indicates the bicyclic nature of this. So means 2 ring, that is 2 rings. So 2 ring plus 1 double carbon-carbon double bond, it gives the double bond equivalent 3. Okay. Now next experiment was done to prove that it contains this 4-membered it contains the four-membered, one of the four-membered cyclic ring, and one of this six-membered ring is also present over here. So if we see, then this alpha-pinene, was treated with ethanolic H2SO4. It was treated with ethanolic H2SO4. Then it was found that this get converted into alpha-terpenoid. It was converted into alpha-terpenoid. Okay. Now, what this reaction indicates? So if we see this alpha-pinene, it has a formula C10H60. Whereas this one, this alpha-terpenoid, it has the formula C10H18. Double bond equivalent, if we have seen double bond equivalent, this is equal to 3. Whereas if we find the double bond equivalent, then it is equal to 10 minus 18 by 2 plus 1, that is equivalent to 2. So double bond equivalent, that comes out to be 2 here. Now, what this reaction indicates? So first thing, it tells the formation of this alpha-terpenoid. It tells the presence of one six-member ring having a carbon-carbon double bond, because here this one carbon-carbon double bond is present here. It means in alpha-pinene also one carbon-carbon double bond that should be present. Okay, so this double bond equivalent, what it shows? It shows one carbon-carbon double bond and one ring, and one carbon-carbon double bond that can be proved by the either hydrogenation or this bromination reaction that can be proved. So it means this reaction, it indicates the presence of a six-membered ring. The presence of six-membered ring. Six-membered ring. Okay, indicates the presence of six-membered ring having the position of this double bond, having one carbon-carbon double bond at this particular position. Next thing, so as here this is monocyclic and this is bicyclic. So here it means one of this OH group is also present, and this formula contains this oxygen. So that it means it was proved that this has one of this oxygen corresponds to one OH group. Okay, and this is a tertiary OH group. Now this tertiary OH group, as this is a bicyclic, this is a monocyclic, it means this bicyclic is converted into the monocyclic, or we can, in reverse direction, what we can think that this OH is somewhere involved in the formation of a bicyclic ring or four-membered ring in the alpha-pinene. So OH of this alpha-terpenoid is responsible for the formation of four-membered ring in the alpha-pinene. So next, one of the conclusion that we may draw from here is this OH of alpha-terpenoid. OH of this alpha-terpenoid is involved in the formation of four-membered ring in alpha-pinene. So how can we say it? So if we see this OH, how can we see that how this OH is involved in the formation of this four-membered ring? Let's see it. Suppose this is our alpha-pinene, this is our alpha-terpenoid, and this alpha terpineol, I may write it like this. I may write this alpha terpineol in this fashion also. So just I am inverting this group upside. So I am inverting this group upside. OH. Okay. Now this OH is involved in the formation of 4-membered ring. So this OH is involved in the formation of this 4-membered ring. Okay. So how it can form 4-membered ring? How it can form 4-membered ring? So this 4-membered ring, either it may be formed in this way. So 1, okay, this is 1 and 2, 3, 4. So either the 4-membered ring can be formed, the removal of this OH group will take place, and 4-membered ring can be formed either in this, or if we want to form a one ring. Suppose if we want to form a one ring, then as this is a bicyclic, so the second ring can be formed. I am not talking about only the possibility of formation of 4-membered ring. So this OH may be involved in the formation of ring, and it may be either 4-membered or it may be 3-membered. So let's see which is correct. So this OH, after this removal of OH, one of the ring that can be formed from this carbon, another ring that may be formed using this carbon, and next ring that may be formed using this carbon, and next one using this carbon. Okay, so let's see how. So suppose I may write one of the possibility. So OH that would be removed, and after the removal of OH, one of the ring is formed in the α-Pinene. So this can form the ring like this. This is one of the possibility. Next possibility, that it may form ring by using this carbon. It may form ring by using this carbon. And third possibility that it may form ring from this carbon, and next possibility, it may form ring by using this carbon. Okay, so 4 centers are there through which the 4-membered ring can be formed. Either this is one of the center, this is another center, this is another center, this is another center. The ring may be formed using these 4 centers. Now, so out of this 4, which is correct? Out of this 4, which is correct? So this is, suppose, first possibility, this is second possibility, this is our third possibility, and this is our fourth possibility, which is correct. So if we see that this one of the possibility that was rejected, so this was rejected. So first possibility was rejected because the 3-membered ring being the strained ring, so that's why it was rejected. So this was rejected. Here also, this is also rejected because it is also forming the 3-membered ring. So this is also rejected. Now let's see this third and fourth. Now if we see the fourth one is also rejected because it forms a ring from the bridged carbon, and this bridged carbon, this is a bridged carbon, which contains a double bond. So bridged carbon, if it contains this double bond, then that is unstable. So this is unstable due to the Brett's rule. By Brett's rule, this is unstable as the bridged carbon should not contain the double bond, and it means only this one is the correct proposed structure. So the formation of this four-membered ring, or this four-membered ring, that was proved by the pairs. So let's see how this four-membered ring was proved by the pairs. Okay. So pairs proved that this alpha-pinene contains the four-membered ring. So let's see. So Bayer's experiment. So it was done in 1896. So how it was proved? It was proved when this alpha-pinene, this was the structure for this alpha-pinene. Suppose this is the structure of alpha-pinene. So when it was treated with, when alpha-pinene was treated with 1% alkaline KMnO4. When it was treated with 1% alkaline KMnO4 in cold condition, then it forms the pinene glycol. It was forming the pinene glycol. So this OH group that would be attached over the double bond. So this is one of the OH group, and this is the next OH group. So it forms the pinene glycol. Okay, it was forming the pinene glycol. Next, again when it was treated with hot 1% alkaline KMnO4. Then what happened? This bond gets broken. Okay, this bond will broken down from here. Suppose it breaks from here, and then it was forming here. So this carbon that will be converted into keto, and this carbon that will be converted into this aldehyde. So suppose after breaking, what we can write? We can write like this, or we can understand it. Suppose, so one of the OH is present over here. So after breaking it, okay, we can add two OH group and this OH, and now remove the H2 from here and remove the H2 from here. Already one of the H is present over here. So what it will give? It will give you the keto group over here, and it will give you the CHO group over here, and further it will get oxidized by this KMnO4, and we will get a COOH over here. Okay, so what we can write directly, I am writing over here. What we can write a keto. So this carbon that will be converted into keto, whereas this carbon that will be converted into COOH. First of all, it will be converted into CHO, and further it will be oxidized to acid. Now, so this was called as the pinonic acid. Okay. Now, further, it was treated with Br2NaOH, or we may write a NaOBr, sodium hypochromite. So this is the reaction. This is our haloform reaction or bromoform reaction. So haloform reaction, and we know that in haloform reaction what is formed? So this here, this OH base that will take out one of the hydrogen from here. So this, it will extract one of the hydrogen from here, and again second hydrogen and third hydrogen, and like this. So it would be, and finally this bond that will be broken from here, and this will get oxidized, this will get hydrolyzed, and it will be this CH3, this CH3 is converted into CBr3, and after hydrolysis it would be converted to H, that would be added over here, and OH, that would be added over here, and what we may write, that would be converted into, means one of the, this halo form, that is bromo form, that would be formed here, CHBr3. Bromo form that would be removed. This carbon is one carbon less, and it gives a acid having one carbon less, or the product having one carbon less. So finally, and what we will get? We will get here a COOH. Okay, so this keto group, that is then hydrolyzed to COH, and this is our COOH. Okay, so this was called as the pinic acid. This is called as the pinic acid. Okay, dicarboxylic acid. And here this is the one keto group and COH group, that's why it was called as pinonic acid. And containing these two acid group, that was called as the pinic acid. Now this was further it was oxidized. So this pinic acid was further oxidized, and in presence of PbO2 it was oxidized. And in this here, this bond will get broken, and finally it was giving the COH, and this is COOH, and one of this HCOH that was removed from here. So this is called as this was called as the norpinic acid. This was called norpinic acid. And this I have written the cis norpinic acid, and it also gives the trans norpinic acid, or we may write a trans norpinic acid in this way. We may write trans norpinic acid like this. This is the trans norpinic acid. Okay. So the formation of this reaction, it tells that alpha-pinene. This reaction tells that this alpha-pinene, it may gives you the alpha-pinene was giving the 4-membered ring. So this reaction tells, this Beer's experiment tells the presence of a 4-membered ring. So the presence of 4-membered ring, it was further confirmed by the synthesis of this cis norpinic acid or trans norpinic acid. So let's see the synthesis of, let's see now the synthesis. So synthesis of this norpinic acid. Norpinic and it was given by Cat in 1900 and I think in 26 or something like this. Okay, it was given by Cat. Now, so for this to synthesize this norpinic acid, one of the this reactant that was taken, that was the acetone, and this acetone is in presence of cyanoethyl acetate, okay, or ethyl cyanoacetate, and this ammonia. Okay, so this was giving, so this being the active hydrogen, so one of the hydrogen, and that will be removed from here, and first 2 molecule of this may attack over here. So this one molecule, and again this second molecule can get attacked, and we may write the product that was obtained. Okay, so here on this acetone, so one of the this, that is CN, it is, and this was CO, this from this carbon, this COET, okay, so it was giving the COET. Similarly here also CN, and this COET, and finally in presence of this it was giving the this NH and this one and this. So this here, this ethanol, the removal of this ethanol that will takes place from here, removal of 2 ETOH molecule will occur and we will get this. Okay. So again second molecule of this, so 2 molecule of this that will react. So 2 molecule of this is a that will react to give this one. Now further, okay, now what we have to synthesize? We have to synthesize norphenic acid containing this 4-membered ring. So these are the 2 carbon which are present over here. Okay, so this has been already present. Now we have to close this ring. We have to form a 4-membered ring over here. So this 4-membered ring that was formed by taking this iodomethane. Okay, so this iodomethane was taken, and so in presence of suppose sodium ethoxide and this one. Now this sodium ethoxide, okay, here it will take out the acidic hydrogen from here and it will give you the minus charge. Similarly, one acidic hydrogen is present over here, it will give a minus charge over here. So the sodium ethoxide, it will remove the acidic hydrogen from this position, and the CH2OH, now this will attack at here, and one of the is I2 that will be removed. So we may write here I, and one of the I2 that will be removed. And finally, that what we can write, we may write here Cn and CH. Okay, and in next step, this minus charge that will again it will attack over here, and this I2 that will remove, and we may write here so we have got something, a structure that resembles something like this, and now we may convert this one. So now we may do the one of the Cn is attached over here, Cn. Now if we do the hydrolysis, again if we do the hydrolysis, suppose if we do this hydrolysis, then what we may get? So hydrolyze it. Hydrolysis, what will happen? This Cn that will get hydrolyzed to carboxylic acid group. This will also get hydrolyzed to carboxylic acid group, and here this bond will break, and here H, this is OH, this will be that OH, and this will get also hydrolyzed, and finally what we may write the structure Cn, and this would be COOH. Sorry, this would also be converted to COH, and COH. And finally, after heating it at 200 degrees Celsius, so this is dicarboxylic acid, and as the COH group are attached over the same carbon, so that's why only one carbon that will be removed, because this only one carbon that will be removed by the decarboxylation. So 2 molecules of CO2 that will be removed from here, and we will get the structure. We will get this structure COH. Okay, so here what I told you, only one COH that would be removed. So why one COH? So if we see, if we have a dicarboxylic acid, then after heating it, only one COH that will be removed. So reason is, so only this one of the O is involved in this hydrogen bonding. If you see this structure, okay, so this is involved in the hydrogen bonding. So one of the this OH, okay, so we may write this as O, and this is H. Okay, so we may write here this. So one of the COH, and this is the another COH that would be. So this is the another COH to this carbon. One COH is attached over here, and another COH. So this is the another COH. Okay, so this is dicarboxylic acid. Now if we see, then here we may see one of the hydrogen bond is present. We may draw a hydrogen bond. This is the OH. So we may write the structure in this way, dicarboxylic acid. We may write the structure in this way, sorry. Let's write this way. And this would be involved in the hydrogen bonding. This would be involved in the hydrogen bonding. So this bond will get broken, and finally this will come here, and finally, so what we can write, so this bond gets broken, and we may write the structure in this way. So H, single bond, and okay. Okay. Like this. Means one of this CO2, as we can see here, this one of the CO2 is removed. One of the CO2 is removed. If two CH groups are present over the same carbon atom, then only one CO2 that would be removed during the decarboxylation. So like this. So in this way, so this synthesis, finally the formation of this morphinic acid that was formed by the CAR, then this was having the same chemical properties, and all these molecular formulas, the chemical properties all were same. So by this it was proved that this alpha-Pinene that contains one double bond, and it contains 10 carbon, and it is a cyclic monoterpenoid, or we can say it is a bicyclic monoterpenoid. So now finally the structure of this alpha-Pinene that was given, that was proved by its synthesis. So in my next lecture I will tell you the synthesis of this alpha-Pinene. Okay, thank you.